Okay, so today we have a lab. Tomorrow we've got a quiz test. It'll be a test testing two things. One, your ability to differentiate. So, using the product chain, quotient rule, doing all kinds of things, right? So hopefully we had plenty of practice at that. That's good. And then the second thing we'll be testing will be, that whole process of finding local max and mins, finding inflection points, and finding global max and mins. Okay, so what you need to know is you need to know how to differentiate functions, and then you need to know how to set them to zero, find critical points and inflection points, and then be able to analyze them to see whether they're max or mins. Okay, so that's the basic thing. A graphing calculator does help, right? So because you can use that to double check that you've got the max or min, that whether it's a max or min correct. So that can be used. But you have to show work on your thing. So yeah. Any questions about anything about the test tomorrow? Okay.
Is there going to be stuff about with finding derivatives as well?
Sorry?
Is there going to be something differentiating, or is it just like...
It's going to be one half is going to be differentiating, one half is going to be, yeah. But also to find max and mins, you need to be able to differentiate. So it's all a compact ball. It all fits together. Okay. So let's talk about today's lab. So another bit of assessment is that there's going to be a project due at the end of semester. So you're going to pair up and look at some problem. You're going to have to model it somehow and come up with some answers. So one of the things you should do, you should think about who you're going to partner with. So maybe, I was thinking that maybe after the break, I'll assign out projects, and then you can tell me who you're paired up with. So that's one thing that you should start thinking about, is who you're gonna work with. So here's an example of a modeling problem. So let's have a look, think about the population of the US. So if you think about it, that's something kind of obvious that you want to be able to model. So you want to be able to predict what the population is going to be in 5, 10, 15, 20 years, because you have to figure out, roads to build, schools to build, that kind of stuff. Where to put services, what infrastructure to put in, etc. Okay. So we already talked a little bit about population growth right at the beginning of class. And there, I told you that, the most basic way that you can model growth is exponential growth. And if you think about it, that should make perfect sense, right? Because if you have a population, how's it going to grow? Well, it grows because you have births, right? And so the actual growth is births minus deaths. Okay, and so a simple model would be is that the number of births and the number of deaths is proportional to the population. That means, if you've got 10 times more population, then you've got 10 times more births, 10 times more death. So 10 times more births minus deaths, so 10 times more growth. Okay, and so we know that constant relative growth, that's exponential. So let's have a look at the US. So the US is nice, right? Because we have a census every 10 years. We just had one last year. Does anyone know, when's the results of that coming out? It
was delayed.
Yeah, right. But but it should be coming out sometime soon. So for 2020. So, but it's in the Constitution that every 10 years there's a census, and so that, you know, this is back in the 18th century. They realized that you need to know the population because you need to know where to put the building, how to, you know, apportion representation in Congress, all that kind of stuff. So the census is super, super important. Okay, and so what I've got here is, I believe the first census was it 1790? Yes, 1790. So here I've gotten 1790, 1800, 10, 30, 40, 50, 60. Well, this is from 1790 to 1860. Okay, and this is the results of the census. And so here is, you know, it's like started off at 3.9 million, and by 1860 it was 31.4 million. And so here, I think in blue is a line sketching the population of the US. And so let's fit it with an exponential model. So remember what the exponential model says. It's going to be population at time t equals p naught e to the kt. Everyone remember that? Okay. So there's two parameters. You've got to have a starting point, p naught. So that's kind of like what is the y-intercept in this case here, and k is the growth rate. Okay, so if we can think of it like interest rate, it's like the continuous interest rate, you know, the population. So here I made a little guess, like I said, well, let's have P naught be 3.9 and let the K be 3%. So we're thinking of the US population as growing at 3% per year. Pretty simple, right? And we get good fit. Okay. Let's try and get a better fit. So let me give you a little sidebar about how do you decide whether one model is better than another model. So what you've got to do is you've got to have some criterion where you say, well, this model is better than this model because it satisfies some criterion. And there's actually lots of different criterion that you can use. But the one that people like is the least square criterion. So has anyone done Stat 190? So you would have done that in there. Yeah, we're not going to go into. So actually, with the least square criterion, we can think of it as a global minimization problem. So what you want to do is you want to choose parameters such that the sum of the square of the errors is minimized. You want to find the global minimum of that. And you can do that with formulas and do that, but we're not going to do that today. That's what you would do in a stat class. Instead, we're just going to do a little bit of what I call hill climbing. Hill climbing actually refers to finding maxima, but it's the same principle for finding minima. So basically, you think of yourself in some landscape of parameters. You know, that's what varies. It's not X and Y. It's like whatever your parameter space is. And you just walk up the hill that gets you towards optimization. Okay. So you're in a spot now and you figure out, well, that's a better spot, so I'm going to walk in that direction. And then eventually you decide to stop. So it's a very simple kind of algorithm. So let me show you how it works in this situation here. So here is the population, the actual, that's reality. And here is what the model says. Okay. And we see that it fits pretty good. And we can see that because the red and the blue are almost overlaid. But what I then do is that I do 3.9 minus 3.9 is 0. This minus this, and then I square it, I get that. And so this thing here is just this minus this, the difference, and I then square it. The reason why you square it is that it's easier to work with when you come up with formulas. But we're not doing formulas, but we're still going to use the least square criterion. And then I add them all up. So this is the total error of the model, and it's good because it's a single number, right? You want things to be a single number because then you're just trying to make that number as good as possible. And that's the whole idea. So this is why they do this thing, because you can reduce how good the model is to a single number, and then you can just try and get as good a number as that. So what I want you to do is open up that file and then just sort of play with parameters here. So play with 3.9, play with 0.03, change it just a little bit, and see if you can get this this error, some errors to less than 0.1. Okay, and do P0 to 2 decimal places and K to 4 decimal places. And what will happen is that you'll change one by a little bit, and if it makes it better, keep it. If the change makes it worse, go back to where you were before and try a different direction. So the idea is you're testing directions and you're trying to find things that are best as possible. So I'll let you play with that for a few minutes until someone gets something good. Has anyone found anything better? Keep going. Just change things a little bit. Sorry?
That sounds slightly better. You said you wanted below 0.01, right?
0.1.
Oh, then yeah.
Did you got below 0.1?
I'm sorry, I had 0. Sorry.
Hmm? You got something? Okay. What'd you get, Matt?
0.029801.
29801.
801.
Hang on, sorry, 0.029, right?
Yep.
That's your K. And what did you get anything different for P0?
No, that was the same.
Okay.
And the percent error was 0.07.
0.07. Very good. So that's it. It's just like a little game we've made up. Okay. Okay. So we get so this seems to be a more accurate growth rate. So let's put that in 29801. Did I do that right? Oh, I've got too many nines, don't I? Oh. Hang on, is that right? But you've got 0.0, oh yeah, 0.07. Yeah, okay, good. And do we get any better if we
3.89 helps me for the
3.89? Oh, that's a little bit better. So at some point you've got to stop, but I mean these are all good. Okay, so let's. And so we get here a very tight model. Okay. Okay, anyone know some US history? What happened in 1860? The Civil War, exactly. So that's going to probably put a dent on things. But also, what's happening in US history back then? So 1790, whatever, we started off, how many states were there then? Like 13 or, not many, right? It was the original 13. Maybe Vermont has joined. I can't remember when Vermont joined, but from 1790 to 1860 was right the westward expansion, right? And so the population was very free to grow. You know, it just people just set out for new places and set up whatever. Okay, so we start to suspect that maybe our model might not be so good in that situation, because like if there's constraints to the population growth, maybe the population isn't free to grow exponentially anymore. So there's a second model. So this is the first model. This is exponential growth. There's a second model called logistic growth. This is also called Malthusian growth. People heard of Thomas Malthus? He's a famous, well, he was he was a clergyman sometime in the 1700s, and he was the one who said that, oh no, you know, like population without constraint is just going to grow, and we're all going to end up starving to death. You know, it's going to be terrible. And that really, he was a very influential thinker. People worried about these kind of things. So one of the person who worried about that was the King of Denmark, because he was thinking, wow, I live next to Germany, and if things get rough, I don't think we're going to come out so good. So sometime in the 19th century, he said, is this true? Is it exponential growth going to be what's going to happen? And this Belgian scientist Verhulst said, well, maybe not, because what will happen is you can't, his idea was you can't have constant K, right? Because as the population gets bigger, resources get scarcer, the death rate's going to go up because, you know, people are going to starve and whatever. But also the birth rate is going to go down because if times are hard, people are going to have like less children, sort of thing. So his idea was that the growth is going to be, so instead of having a constant growth rate, the growth, so this is Malthus. Verhulst said, maybe you'll have a growth rate like this, right? So that it starts off at the same level as here when there's hardly any population around, but as it proceeds along, the growth rate drops linearly as respect to the amount of population. Okay, and if you go ahead and do that, you get the following logistic equation. Okay, so what I'd like you to do then is close the file that we worked on now and open up the file logistic. Okay, and this is what earned Verhulst a gold medal from the King of Denmark, this model. And you see, what do we see? We see, like here, when the population is low, we see kind of exponential kind of growth. But then after a while, it goes from concave up, which is what you expect with exponential growth. After a while, it becomes concave down, and it seems then to plateau off. Okay? So in this scenario, we have three parameters, L, C, and K. Okay. L is what we call the carrying capacity. So has everyone opened that file? So change L to different numbers and see what happens to the curve. And so where do you notice L appearing in the graph? Right. So you can maybe you can see why it's called the carrying capacity. So basically, L is kind of the population that the environment can support. So you've got the land, the water, the food, the resources, whatever, to support that amount of population. And so in the long term, you're just going to settle in this population at this population level. And what can you tell me about births and deaths? They're equal, right? The population doesn't change. That doesn't mean the people don't change. But it just means that the rate at which people are born is offset by the rate at which people die. Okay, and this has kind of been observed in actual real life, that this kind of thing happens, that populations get to some sort of stable point like this. Okay, I don't think I want to go too much about what the other things are. K here turns out to be the growth rate when the so it turns out that when the population is small, you can approximate this to some e to the kt for population small. Right, so this k is the same thing as the growth rate, and this c thing here, it's hard to come up with a nice meaning for that. It's just what you need to it's kind of related to the initial population. It's not exactly that, but there's a relationship between C and P naught. So that's what you can think about that. Okay, so this is our new model. Okay, and now that we've done what we've done in chapter 4, can anyone tell me what this point is here? It's an inflection point. And logistic, so there's only really two things you need to know about the logistic curve. One is that L is like the saturation is its maximum level, and that the inflection point always happens when the population is half the carrying capacity. So when the population is below the half the carrying capacity, the growth is kind of like exponential. And when the population is below half the carrying capacity, it's sort of tapering off to that level L. So that's really the only things you really need to know about the logistic curve. Okay, so let's stop that and, oops, I don't want to save that. And let's go to US2. Okay, and let's change K to what? 0.029801, and P naught to was it 3.89? Okay, so what do we got here? So what happens now is that I put in more US census data, and I'm 1790 here, 150 years later, we're in 1940. Okay. And let's see how our model then compares to the reality. So here's exponential growth. And we see, here is 1860. We have this nice fit here. And then all of a sudden, the exponential growth is going off as exponential growth does. But this is the real population. So do we see evidence of constraints to growth? Yeah, because we're not following the exponential growth anymore. So we're seeing evidence that we have logistic growth models. So that is a more appropriate model then to use. Okay. So we have to replace our model with this. Okay. So the first thing we have to do is we have to think of, let's think of an L. So what do you think the carrying capacity could be based on this? Just a rough guess.
So you might be like 150 or so.
150. Okay, so let's put in L of 150. Okay, and so here, C, I've already put in the relationship between C, L, and P naught. So don't touch the C thing because that'll screw things up. So let's replace the model by the logistic model. So scrub it out, and what's it going to be? It's going to be L, which is $2 divided by, and then in brackets, we want to put 1 plus C. C is $2 times, times exponential is EXP. In brackets, we want to put minus K. K is $2 times the time, and the time is A2. So don't put dollar for that because it's going to change. Close bracket, close bracket. Oh, and you should get 3.89 back. So that's great. And then we just copy and paste it. And then I can't see what this is doing anyway. Okay, and so straight off we see that I've made a big improvement with the model, right? Before the error was like 60,000, and I've put the model down, the error down to 2,800. And we see that there's still room for improvement. So has everyone been able to get this? Okay, now it's a new game. Let's try to get the error under 100. So do that by just changing these three things, P naught, K, and L. Don't touch C because C, I've got a formula for C that's based on P naught and L. So try changing those three things and trying to get error as good as possible. Does that make sense? And so the trick is just to do little changes, just to find the direction in which the thing should increase. So if I remember right, I think K should be a little bit higher. So we can start working on that. Someone yell out when they've got under 1,000. So what did you get for?
For P0, I had 3.885.
Okay.
And then for K, I had 0.3034.
Yep.
And then for L, I had 150.
And what's your error?
It was like 260.
260?
It's like 259 point something.
Okay. You can make it a little bit better. So everyone go there and play with it a little bit more. Okay. We're getting L up to 156. I've made the error under 200. So you can see, sorry?
I thought mine was 160.
Okay, what was your value for P0?
197. Or P0 is 3.887.
7. Okay,
Well, my total errors was 197, but I was saying I put my L to 160.
160. Oh, no, it's best if it's a little less than that, isn't it? Oh, hang on, what was your K?
0.0341.
Hang on. So what am I, so you got it under 150. So what am I getting wrong? Hmm?
Never mind. I didn't get it under 150.
Okay. I thought you could, oh, okay. Oh. I got it to 180. So but anyway, let's just stop there. I got it to 180. I'm pretty sure you can get it to under 100. But anyway, so this is okay. So this is pretty reasonable. So we can see it's much closer fit. Notice that it's impossible to get error of 0, right? Because that would be perfection, and that real life never does things exactly right. But this is kind of interesting because it makes a prediction about the US population. It's showing that the population that US can support is 158 million. Is that wrong? Well, I mean, what's our population today? It's like 300 million. So that's of course, so what's suppressed this model? So think 1940. What's around that's making life bad for us before 1940? Right. So, and in fact, we can see the effect of the Great Depression right there, right? You can kind of see that the model is going kind of like this, and then it's kind of there. So there's historical events that are going to affect. And in fact, we know that this picture then of it going to 158 million is false, because what happens after 1940? I'm thinking more in the 50s and the 60s. What happens then? What happens to the economy in the 1950s? Is it good or bad, the economy after World War II?
It's good.
It's good, right? So people talk about the post-war boom. Okay, so we won the war, beat the Nazis, thank goodness. And after that, so the Great Depression was left behind. There's all kinds of startup technological sort of benefits. So war is bad, but one interesting thing that it does is it stimulates technology and industry. So, and then after World War II, there was a lot of rebuilding. There was like all these plans, like in Europe. So there was a boom in the economy just from sort of rebuilding. Okay, and so finally, let's look at US 3. And okay, we see evidence then of another change in US history. So these things are interesting, right? Because you can actually see history in the map. You can see that there's actual events that bring about these things here. And so we see that this was kind of like a false leveling off, right? Because it was induced by the Great Depression. We were thinking that, oh, the country's going to be small, but instead the country came out of depression, went into a boom, and we can kind of see that it's sort of heading off right there now. Okay, and so here's a mole, here's the error. So we're back up to a large error again. So just in the few minutes left, so this is up to 2010. So So the next time I do this course, I'm going to have to introduce another row when we get these figures out. So yeah, we're up to 308 million. So just play with that a little bit and let's see if we see how. I think if you can get it below 1,000, you're doing good. Have a go again. The same thing. P naught, K, and L. So anyway, I got it to around 5,000. Did anyone do any better? 5,500?
2,700.
Oh, what was your figures?
4.2.
4.2?
Yeah.
Wow, okay.
0.028.
0.028?
Yeah. 330.
330. Oh, good. Excellent. Okay. So according to this model, we are pretty close to maximum capacity for the US. That's interesting. I mean, that always gets you into a very interesting political discussion about immigration. Anyway, so that's the logistic model. So, yeah, okay. So see you tomorrow for the test. And that's it, yep.